In this lesson, we'll learn about the mass spectrometer and its usefulness for what we are studying. And we'll also learn how to determine the percent composition of a compound. A mass spectrometer is an instrument that's used in order to help us to determine the molar masses of atoms or molecules in a sample. The way that it works is that a gaseous sample is bombarded by a high-energy stream of electrons, producing cations. These cations are then passed through a charged plate, series of plates. When they pass through the plates, they're deflected to different extents, and they're deflected based on their charge and their mass. Ions of a smaller mass are deflected to a greater extent. So in this particular detecting screen, the ions that would be observed on the left-hand side are the ions of the lower molar masses, while the ones on the right-hand side are ions of higher molar mass. This is useful to us to determine the molar mass of molecules, which we'll be using later on in the unit. It's also very useful to us in order to help us to determine the isotopic abundance of a particular element. The different quantities of isotopes in a particular sample will produce different amounts of detections on the screen. The more current that's observed is relative to the number of ions in the sample, and how it will appear in a spectrum is with a higher peak. In this mass spectrum that you see here, it's the mass spectrum of neon. And what you can see here is that there are 3 different peaks, each representative of the different isotopes of neon. Neon 20 with an isotopic abundance of 90.92, neon 21 with an isotopic abundance of 0.26, and neon 22 with an isotopic abundance of 8.82. So as you can see, the peak height is relative to the abundance. Okay. And they've all been deflected at different extents, and so that's why the peaks are spread out on the spectrum. Neon 20, with the lightest mass, would have been deflected to the greatest extent, and so would have been detected on the left-hand side of the screen. This particular spectrum is a great example of how improving technology can help to improve our understanding of what exists in nature. As mass spectrometry improved, we were able to identify or see isotopes that were not previously known about. Neon, for example, in the initial stages of mass spectrometry, was thought to have 2 isotopes, neon 20 and neon 22. But as the precision of the equipment improved, we were able to detect neon 21, which, as you can see, has a very small peak, so is much more difficult to detect. The next item we'll discuss in the lesson is percent composition of compounds. The percentage composition of a compound is the percent by mass of each element in that compound. And this can often be determined by doing different types of experiments. It can also be determined from the formula of the compound. So we'll look at how to do it with the formula of a compound. As you know from our previous discussions, the percent of something is the part that we are analyzing divided by the whole times 100. So when we want to look at the percent composition of a particular compound, and we want to look at the percent of each element, we're going to look at their individual contributions to the overall mass in order to determine their individual percentages. We'll do an example where we determine the percentage composition of magnesium hydroxide. So it's important to note here, when you're asked for percentage composition, that you're being asked for the percent of each element in that compound. So we need to know the percent of magnesium, the percent of oxygen, and the percent of hydrogen. Okay? And any sample of magnesium hydroxide is expected to have this same percentage composition. Because we are able to work with a mole of magnesium hydroxide, we know the mass of 1 mole of magnesium hydroxide. So we're going to use the molar mass to help us to determine the percentage composition. The molar mass of magnesium hydroxide, as determined using the values in the periodic table, is 58.33. Now we want to be mindful that we're going to take the sum of all the individual molar masses, and we want to take into account the fact that there are 2 oxygens and 2 hydrogens. To determine the individual percentage compositions, we're going to take the percent based on their individual contributions to the total mass. So magnesium, there's 1 magnesium, so it's got a molar mass of 24.31. And we're going to take that part, divide it by the entire molar mass, which is 58.44, and we're going to multiply by 100. So we get a percentage of 41.67. Now for the oxygen, we've got 2 oxygens, so the contribution of the mass by the oxygen is 2 times 16. So we're going to take the part that's oxygen, or the molar mass of the element, times 100 divided by 58.33. And that gives us a percentage of 54.86. To determine the percent of hydrogen in the compound, we can do the same thing by determining hydrogen's contribution to the overall mass, which is 2 times 1.01. We're going to divide by the molar mass, which is 58.33, and times that by 100. And that gives us 3.46. When you've got 3 elements like this, another way to determine the percent of the last element is to take the sum of the previous ones and subtract from 100, because we know that the percentages will all add up to 100. I like to do the long way, which is this, determining each of them individually, so that I can check my answer at the end. Okay? Because if I've done everything correctly, then my percentages should all total up to 100 or very close to it. In this case, I find that my sum is 99.99%, which is very close to 100, so I'm very happy with that value. Okay? And it's normal to have something that's not exactly 100 because of the rounding that we've needed to do in collecting our data from the periodic table. Another type of question that you might encounter when you're dealing with percentage composition is one like in example 2. It asks you to calculate the number of grams of manganese in 150 grams of potassium permanganate. So we have a sample of potassium permanganate, and we want to know how much of that 150 grams is manganese. This is very useful, okay, because if we wanted to do something to extract the manganese and use it for something else, we would know how much manganese we would have access to. We can use percentage composition by first determining the percent of manganese in a sample of potassium permanganate. So just like in the last example, we're going to take the molar mass of manganese in the compound, which is 54.94 because there's 1 manganese, and we're going to divide by the molar mass of the entire compound. So again, I'm going to take the molar masses of the individual atoms, from the periodic table. I'm going to add them together. I get a total molar mass of 158.04. I'm going to times that by 100. So what I find is that in potassium permanganate, the percent that is manganese is 34.76%. And this percentage will be consistent for any size sample of potassium permanganate. So therefore, to find the mass of manganese, I need to find 34.76% of 150 grams. So as you know from math, if you want to take the percent of something, you need to divide your percentage by 100 and times it by the quantity. So what we find in this case is that the mass of manganese in this sample is 52.15 grams. There are some questions out of the textbook that you should do, practice exercises 8 and 10 that are found within Chapter 3. And then number 39, 41, 42, and 46, which are found at the end of the chapter. Not all of these questions are going to be exactly like the types that you've seen, so it's really important for you to take the time to do the questions assigned so that you can see what types of questions you might encounter.